1, 0, and liftoff.
Expected this body to be rather like the moon. This was quite an interesting discovery. It was one that we thought we might find.
Command Center for the Deep Space Mission, which in the past few days has carried the eyes of men farther than they've ever been.
And the science is pushed in.
Just last night, we had these frames come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour. Good morning. Welcome to the 9 o'clock edition of Voyager Update. I'm Al Hibbs, and at 9 o'clock a.m. Pacific Daylight Time, the Voyager spacecraft is 2,230,000 kilometers, or 1,386,000 miles from the cloud tops of Neptune, and speeding toward the planet with a speed of 37,855 miles per hour relative to Neptune. We hope to hear all is well with the spacecraft, and to that end, we'll talk to our regular morning guest, Lanny Miller, and manager of the Voyager Flight Engineering Office. Good morning, Lanny. How are things?
Things are just fine.
Very good. What has been happening, by the way? We've sent another series of update commands to the spacecraft?
Well, we're going to send a series of update commands to the spacecraft this morning. In the last 2 days, we've been a very active round-the-clock period developing what is called the late ephemeris update. Ephemeris means the path of the spacecraft, and we are updating the sequence for the near encounter based on the very latest trajectory information that we have gathered. And that load has now been successfully generated. I just came out of the meeting that approves that load to be uplinked to the spacecraft. That uplink of the entire near encounter load will occur just after noon today.
And does the latest ephemeris show that we're pretty much where we want to be as far as the trajectory
We are
goes?
in very good shape. Just following, or just before that meeting, we had another navigation meeting that is for the late stored update, which is an update to this sequence after it is already on the spacecraft and running, and will be uplinked tomorrow, just before we get to the planet. And we have determined that the nav data shows that we now have 35-kilometer accuracy and 2.5-second accuracy in the time of flight. We now know that we will arrive at the planet about 4 minutes and 20 seconds early compared to what was planned at the so-called 9 o'clock Pacific time arrival. So we're 8:55, 40 or so.
And the plan we're differing from was made years ago.
Years ago. And the reason that we're not right on time is that the planet is a little bit closer to us than we had estimated, because we know
it's not our fault, it's nature's fault.
That's right. Well, it's an artifact of the fact that the planet has a very long orbital period, 165 years, and was discovered only 147 years ago, so we've never seen it in this part of the orbit before. So it makes it difficult to precisely pin down where it is, and now we're going to know very precisely where it is when we fly by it. So
what about the trajectory correction maneuver that was done in order to get exactly behind Triton from our point of view, the Sun-Earth occultation requirement? How'd that go?
That went extremely well, and that's the estimate on that from this morning's navigation meeting is that we now will achieve both the Sun occultation and the Earth occultation, the so-called dual occultation, behind Triton with a probability of 99%.
That's extremely good data then that we're getting on it.
Extremely good, and the fact that we did the roll turns TCM and that didn't put the heat perturbation into the receiver, in fact all worked fine and allowed us to get immediate navigation data, and without that we would not have been able to
get the
certainty that we are, and we would not be able to then tweak up in this late stored update sequence process that's going to be transmitted tomorrow, we would not be able to tweak up the final pointing and timing, which is what happens in that process, so that we'd be absolutely sure that everything works precisely for the trajectory that we're really on.
Well, some time ago, we put together a computer-generated movie of the operation at Triton based on our plans, and now we're so close to the plans, I think why don't we show that movie, because it's
Great.
It's correct.
Great.
Okay, let's take a look at the clip of the Triton approach. So that's Triton in the background?
That's right.
And the thing is, we want to go behind it from the point of view of both the Earth and the Sun.
That's right.
And take pictures just before that happens.
Well, the UVS instrument will look through the atmosphere at the sun, and the radio science will use the antenna to look through the atmosphere, if there is one on Triton, as well. So the radio science has to look at the Earth, and the UVS has to look at the sun.
And meantime, we're laying down that
We're laying
pattern
down
of
a
mosaics on the surface.
pattern of mosaics on the surface with the imaging camera, and now we're going to go.
Sun
There goes the sun.
and the Earth.
Yes. Now that
What was in the reverse order, actually?
rectangle was
It was both of them.
the UVS slip.
I see. Okay. Well, very good. Lanny, thank you very much for
You're
bringing
welcome.
us this information, and we trust everything continues to work fine.
Sure will.
See you tomorrow. Thank you. So, the status of Voyager, very good shape. Yesterday's press conference, Brad Smith revealed the discovery of an actual ring completely encircling Neptune, in addition to that, what's been called a ring arc. Let's go to the tape clip of the press conference.
You have probably all seen the ring movie images that came down this morning, and many of you I know have noticed that more than one ring could be seen even in the even in the raw images, the so-called ring arcs. And it seemed reasonable that this was indeed the lost ark that our imaging team raiders were looking for. Now you're going to turn on me, right? The answer to that is yes and no. It is indeed exactly in the right place. That's the yes. The no is it's not an arc. It goes all the way around. So it is Neptune's first complete ring.
Well, we hope to hear more on this discovery at the press conference today. We reported last night, of course, that Voyager's going to have a busy night of observations, so let's take a look at some of the images that came in last night. I think first of all, we're going to picture a disk of the planet. Do we have that up? There we are. And the next image that I wanted to show you was a picture of what are called the scooters in the southern hemisphere. Down the lower right here, you see one of, you see that strange formation that is moving rapidly compared to the others, hence the name. There's another version of it down a little further in another frame that came in. And then the great dark spot, we're getting ever closer and ever more detail. There's one picture of it, and then another frame a short time later where it has moved slightly in the frame. So these are just a few. There will be more discussed, of course, at the press conference. Today the spacecraft will be conducting plasma wave, photopolarimeter, infrared observations of the planet, as well as continuing the imaging of Neptune and the large satellite Triton. I want to remind you, the press briefing this morning, 10 o'clock a.m. Pacific Daylight Time. I'm Al Hibbs for Voyager Update.
Good morning. Welcome back to the science conference on Neptune Encounter. We'll begin this morning with Norm Haynes, the manager of the Voyager project. Norm?
Good morning. As you recall, on Monday morning, I told you we were going to do a trajectory correction maneuver. And the principal reason for doing that trajectory correction maneuver was to adjust the orbit just a little bit so that after it bent over the top of Neptune, it would go behind Triton as seen from both the Earth and the Sun. And at that time, we had an Earth occultation, but the trajectory was outside the Sun occultation zone. We've had a couple of days of good tracking data and navigation data since that time. And so I'm going to show you the results of where we believe the trajectory is going to go at this time. So could I have the first slide, please? The first slide is going to be just a recap of what I showed you on Monday. You'll recall that the blue zone which goes all the way across is the Earth occultation zone, the Sun zone. The Earth occultation zone goes from about here over to here. The Sun occultation zone goes from here to here. So we want to be somewhere in the middle in this crosshatched area. We were out here at the time of the first trajectory correction maneuver, inside the Earth occultation zone, but outside the Sun occultation zone. We did the maneuver and expected to move into this point. Now, what I didn't show you on Monday was the fact that we didn't know exactly where we were at this time. There was an uncertainty as to where we were around there. And so there was obviously an uncertainty as to where we would end up. And what I'm going to show you now in the next view graph is where we believe we are at the moment. Okay, again, this now is that common Earth-Sun occultation zone. We moved from out here into here. We believe this is the final target point that we're going to achieve, and this is the uncertainty that surrounds that point. So in fact, we are right almost smack dab in the middle of the Sun and Earth occultation regions. The uncertainty in the orbits at the moment are when we arrive at when we arrive at Neptune, I'm really back in time. The uncertainty at the moment is about 33 kilometers in the point at which we'll pass Neptune, which is on the order of 20 miles. And our time of flight uncertainty, that is the time at which we'll arrive at closest approach, is about 2.4 seconds. And that propagates now to Triton. The errors are bigger at Triton because when we bend over the top of Neptune, that tends to disperse the trajectory a little bit. But at Triton, the size of this region across is about 150 miles. That's the uncertainty, and we expect that we will be inside that with very high probability. So at the moment, we're predicting essentially a 99.9% probability that we'll get both Sun and Earth occultation. Also today, this afternoon, right after lunch, about 12:30, we will begin the process of uplinking the final command load, which will actually be on board the spacecraft for it to execute its encounter sequence. We'll send that command load up six separate times to make sure that it arrives. We should have confirmation that those commands have gotten in by around 8:30 or 9 o'clock tonight. Once that gets in, then we've got essentially almost the final command load in. But tomorrow we have one more opportunity to, based on even more recent tracking data, to refine very carefully a few of the observations, and in particular the timing of the Earth occultation experiment. We want to get the time of the start of the Earth occultation experiment down to on the order of 1 second. So that's still to come tomorrow. But as of today, we believe that the rest of the sequence will be uplinked this afternoon, and we should be on board the spacecraft tonight. The spacecraft is working fine. The instruments are all operating as we expected, and everything appears nominal. Okay, I think next up is Ed Stone.
Well, needless to say, there are an awful lot of happy scientists with respect to the wonderful job the navigation team has done in putting us right smack dab in the middle of the dual occultation zone. As I've told you, and Brad's told you, we think that Triton must have an atmosphere of some sort, and this means that we will have our full capability to find out what's really there in about 2 days. Okay, just a couple of updates. First of all, I'd like to report that the radio missions, which Jim Warwick reported, I guess on Monday already, indeed are getting stronger, just as they should as we approach the planet. If you have the distance of the planet, they should get 4 times stronger, and it's essentially the kind of dependence which is being observed, and therefore there should be no question at all. The emission is coming from Neptune. It continues to reappear every 16 hours, and we will be able to refine now the periodicity of the radio emission in the next day or so. In addition to that, the plasma wave investigation has also now begun to detect emissions coming from Neptune at lower frequencies. This is at 31 kilohertz. The planetary radio astronomy instrument is detecting them mainly up in the higher frequency band, more like AM radio band. Up to 1.2 megahertz, and as Jim Warwick mentioned on Monday, that means that the field at the location, if I could have the slide please, at the location where the radio emission is coming from is at least 0.44 Gauss. For reference, the Earth's field at the equator is 0.31 Gauss. Now, in this cartoon of a magnetosphere, we don't know exactly where the spiraling particles are that generate the radio emission. What happens is some particles bounce back and forth. Some of them plunge into the atmosphere, possibly causing the aurora, but in the process of spiraling around the magnetic field, they will generate radio waves which can be then detected. The measurement of the field strength is at the location where the radio emission is coming from. For instance, if it's coming from this region, then that would be the field strength there. The field strength varies around the planet. It's twice as strong at the surface of the dipole field at the pole than as it is at the equator, for instance. So we don't know exactly how strong the field is at the equator, but it does appear as though we have a reasonably strong magnetic field. And of course, our first indication of the magnetic field will be this supersonic shock, which stands out in front of the magnetopause itself, the boundary which separates the solar wind, indicated by this blue, and the planetary magnetic field itself. The size of the magnetosphere varies because the wind itself is a wind. It is not constant velocity or constant pressure. It's a wind. And so again, there's just as Brad has been giving you weather predictions for the clouds on Neptune, the plasma team has been making weather predictions for the interplanetary weather. That is the speed of the solar wind and its density, and therefore how hard it's pushing and how much it's compressing the magnetosphere. It turns out that along with the Pioneer 11 data, which is giving us some predictive value, it appears as though the wind speed is slowing down a bit during this time period, and it's somewhat less dense. The result should be that the magnetosphere may be a bit more inflated than otherwise might be expected, and our current prediction is that we might be seeing the bow shock by something like midnight tonight, sometime late today. We might well find the bow shock. That would correspond to a field at the surface at the equator of, say, 0.3, 0.4 Gauss, but we don't know. The field could be larger. Jupiter was 4 Gauss at the equator. Saturn was only 0.2. We now feel it's fairly likely that we're somewhere up in this range, and the higher the field, the sooner we'll detect it. So I think there are going to be a lot of investigators here this evening waiting for the first direct indication of the size of the magnetosphere. So by this time tomorrow morning, I hope that I'll be able to report that we've actually gotten inside. Okay. I'd like to just come back to a topic that we spent a fair amount of time yesterday in question and answer about, ring arcs. Everyone has a theory of ring arcs. But let me tell you what some of the observations are and why there was thought that there might be a lot of ring arcs. The ring arcs were really discovered in 1984 by Hubbard and Brahik and their collaborators when they were doing a stellar occultation. And here was the track of the star as observed from Earth, just like that. And as they were observing the star, at this particular point, there was a dip in the amount of starlight. and it was observed at two different locations, two different telescopes in Chile, separated by 100 kilometers, by 60 miles. So there seemed to be no doubt that they had both detected the same ring material, but nothing over here at all. And then that immediately introduced the term ring arc, because obviously it was not a complete ring. They didn't detect it over here. Now you can see one difficulty with the ground-based observations, which we're now able to resolve, and Phil Nicholson and Dick French have been working on this, and that is, first of all, this particular occultation didn't intersect the planet, so it was and the location of Neptune relative to the star was not very accurately known. So whether this point was here relative to the planet, or up there relative to the planet, or down here, would clearly make a big difference as to what radius you interpreted the point occurred at. And so lack of knowledge as to where Neptune was meant that it was difficult to say how far this point was from the center of Neptune. So that's one kind of difficulty. There were subsequently, this has really been an international effort, starting with, once this arc was discovered in '84, there were international effort to try to track as many stars as possible behind Neptune. A number of investigators in the U.S., Canada, France, Australia, and South Africa have been involved in this effort to try to really determine what kind of material was in orbit. I think there have been at least 21 stellar occultations observed, and here are those few occultations which produced any evidence at all, any reasonable evidence that there was material in orbit around Neptune. And again, each star is shown with the point indicating the best estimate as to where that point is relative to Neptune. Most of these other occultations did intercept Neptune, which gave a much less uncertainty as to their location with respect to Neptune, but there was still one remaining uncertainty which we are now in a position to resolve, and that is the actual tilt of Neptune relative, as we see it from Earth, was not known to within a degree or so. And if you tilt the Neptune a bit, it changes the plane of the rings a bit, and that changes their apparent radius a bit. So there was still some uncertainty as to exactly what radius these arcs were at, because it was not known exactly how much the plane of the arcs was tilted with respect to the observer. All right, so that also added to the complication of understanding how many arcs there were. Now, this is, again, I want to show you the kind of data which the ground-based astronomers get. This is from the NASA Infrared Telescope facility, which is on Mauna Kea. This is the 1985 event, which was observed by Nicholson and his colleagues. It was also observed by Siccardi and his colleagues, also on Mauna Kea at another telescope. Same event, two telescopes, using the Canada-France-Hawaii telescope on Mauna Kea. So this is an event which was, again, verified by two independent observations. Essentially what's done is the same thing we'll be doing with the photopolarimeter on Voyager, and that is one measures the amount of starlight as a function of time as the star approaches the planet. These dips indicate, in this case, and this case, and this case, they're calibrations. And I'll just have to tell you that. That's what they are. They're not anything in the beam of light. Here's the planet. You can see suddenly star blinks out because it goes behind the planet, comes out from the planet. There's another calibration activity. And then there was this dip, which was not the result of any calibration or anything. If it's blown up like this, one can see that the dip lasted a mere 5 seconds or so. And the starlight dimmed by 20%. But it was observed at two different observatories at exactly the same time, so there can be no question that it's a real event. And it fits very well with a model of the ring. The data is the thicker line you can see here, and the thin line is the model fit with a assumed ring width of about 25 kilometers, about 15 miles, and an optical depth of about 7.5%. That is, over 90% of the light comes through the ring. It's rather tenuous. Okay, so that's the kind of observation, and you can see that it's not a complete blank out of the starlight, but it is a measurable, significant dip. Now, I just wanted to summarize for you then, and you don't need to copy these numbers. They'll be handed. I think they'll be handed out to you. But what I've plotted here now, if you could focus this a bit, please. Thank you. This is the distance from the center of Neptune. So Neptune's center is down here, 40,000, 50,000, 60,000, 70,000, 75,000 kilometers. This is where the various ring arcs, as detected by a ground-based telescope, would be located. And the ones with the stars indicate that they were observed by 2 independent telescopes, and therefore confirmed. The others were observed by a single telescope, and therefore are less secure, but nevertheless certainly there were measurable effects at those 2 locations. And this is the reported locations of those ring arcs, and you can see there were 6 of them. Well, with the Voyager observation of the outer arc here and an inner arc here, and as Brad said yesterday, the inner arc does not correspond to any of the measured ground-based data. So that's a new, in fact, it's a ring. That's a new ring. It's too thin to be detected. It doesn't block out enough of the starlight to be detected. And so it does not explain either of these 2. On the other hand, the outer ring, which is quite extensive, but perhaps not a complete ring, maybe just an arc, we don't know, now is totally consistent with these 2 once the correct pole of Neptune is taken into account. And in fact, the current navigation trajectory which we're using is based on the assumption that these 2 arcs are indeed the same as this one, and that gives us our most accurate measurement now of the pole position of Neptune. That was done by Nicholson and French. In addition, this particular ring arc, which is out here, that's this one right here. You can see it's the one where the planet was not occulted, so it's very uncertain as to where it is. It's 4,000 kilometer uncertainty, and it's likely, although one can't prove it, it's likely that it also is this same ring arc. So perhaps all 3 of these were just observations of the same outer arc that Voyager has now imaged. This particular observation, which was the first one, is actually qualitatively different in the sense it's a much deeper block of the sun, of the star, and it lasts much longer. And in fact, when it was first reported, it was reported as the observation of a satellite because it was so deep and so broad. Once the ring arcs were observed, then it would suggest, well, maybe this was really a ring arc after all. But I think now one might tend to conclude that perhaps, especially with the large uncertainty as to where it is, that it might well have been a detection, actually, of 1989 N2. This is a question mark. It has not yet been exactly established, but I think many would now say that this particular arc was not an arc. It was what it was originally described as, that is, a moon. It happens to be that moon. Okay, so that, I hope, helps clarify a bit the confusing situation and why there was the suspicion that there might be many arcs when it turns out that only 3 of them are really just one arc. One of them may well be the satellite, and we still are left with 2 where there is yet still no evidence in the images for that material. Okay. I did want to comment on the photopolarimeter. We do the same kind of stellar occultation from Voyager using the photopolarimeter. We use the star Sigma Sagittarius. It goes by exactly, this is the track of the star. We're very fortunate because, of course, we have no choice. We have to look where the star is. We're very fortunate. It appears as though it will go behind one of the denser parts of the B ring, and will go behind of the denser parts of the outer arc, which is called the B segment, and also go behind the new ring. Of course, the new ring is very thin. That's the reason it wasn't seen from Earth. Lonnie Lane tells me that if the ring is at least 7 kilometers wide, say 4 miles wide or so, and at least 1%, blocks at least 1% of the starlight, that he should be able to detect it. So it's going to be tough, but we have the opportunity. And of course, the resolution, the spatial resolution, especially in this region where there's a fair amount of material, is something on the order of 50 to 100 feet. In other words, the photopolarimeter will be able to map the thickness of that ring very, very accurately. Well, coming events, here is that slide is for some reason not all the way in. Well, maybe you can try again. It's still not all the way in. As a result, it's not in focus. There we go. Good. This afternoon, there'll be a long series of images. These are the wide-angle frames which are placed around the planet, and there'll be a whole series of narrow-angle frames on this portion of the ring system coming down. So those of you who are interested in real-time ring analysis, you'll see it on your monitors. Maybe tomorrow morning you'll have more theories for us. We also, later today, start a very systematic map, thermal map, of Neptune. As I said, one of the important things to try to understand is the weather on these planets. It's not only observing the velocities using the imaging system, but also measuring very accurately the temperature profile in the atmosphere to see if we can correlate temperature variations with latitude with the variations in the wind speeds as a function of latitude. So that will be a very systematic map being made for a number of hours. There will be images coming down during that time as well. And then tomorrow morning, when you come in, we'll be finishing a series of infrared scans, which are latitude scans, very accurate measurement of the variation of temperature with latitude, which is the thing which is key to understanding, helping us understand the winds which we're observing. I think that's it for my slides. And Brad is next. Brad Smith.
Good morning. My colleagues in the imaging team are a bit tired, as might be expected, but they're also very excited, rather boisterous, because the images just keep getting better and better. And the images we're getting now of the cloud features and Triton are getting to the point where we have people literally jumping up and down up there. Let's just look at some of the atmospheric images that have been received over the past day or so. You can have the first slide, please. It's a view of some of our favorite features in the atmosphere of excuse me, Neptune. And I think we missed the first one. Yeah, here we go. These are probably recognizable to all of us by now, the great dark spot with its ever-attendant cirrus clouds, and these cirrus that streak off to the east. This little group of clouds up in the equatorial region, very close to the equator, which have been also just tending to remain in the vicinity of the great dark spot for a number of weeks now, I guess. And that would suggest that whatever velocity, wind speed that we have in the equator, it must be very similar to what we see here at 20 degrees south latitude. Down here is the Scooter, that most rapidly moving feature in the atmosphere of Neptune, this high velocity jet, which is bringing it around at a speed which takes it almost completely, or takes it completely around the planet in approximately 16 hours. And then the second dark spot, which is now beginning to show some structure within. The next slide, which is the one we saw first, are four successive images of the great dark spot. Contrast is a little bit low, but one can see these wispy streamers of cirrus-like clouds, and you can perhaps see the problem that we're having in measuring these velocities, because the change takes place, the change that takes place over one rotation is so great that in many cases it's difficult to decide are, in fact, any of these features exactly the same as any that you can match up here. And if we're to attempt to get these velocities and see where the clouds are moving, to learn something about the vorticity, one has to be sure that they're seeing the same objects. Ingersoll has made the analogy that it's like trying to decide what's happening in a horse race, only you can't watch the horses continuously. You get a view from above, and then perhaps 10 or 15 minutes later, you get another view, but now you don't know which horse is which, and so it's difficult to tell how fast each one is running. And that's the kind of problem that we're running up against with these features in Neptune's atmosphere that just change a lot faster than we had ever expected that they might. Going on to the next
slide, we see here now, looking way down to the south, this very interesting south polar cloud, and we'll be seeing higher resolution images of it today and tomorrow. The next slide shows a color view again of this other dark spot, and we can see a lot of the structure now that's developing within its center. This bright region had sort of subsided in brightness a few weeks ago, and it's coming back now. It's developing and becoming brighter, and in fact we can see changes on successive rotations here where that structure changes, and just about 18 hours later you see it's changed, and then it's changed and changed further and still changing. I don't know whether that bottom one can be seen by everybody or not, but one can see that there are real changes. And can you tip the projector maybe just a little bit to so they can get a quick peek at this bottom slide? Can you hear me up there? Maybe it won't tip. Yeah, there you go. Okay. So you can see the changes, and of course we're interested to understand exactly what's happening. One might assume, just as an assumption, that what we're seeing is a convective system with the atmosphere moving up in the center of this spot and causing condensation up at the top. Now, if that happens, then as it moves out, a force which is prevalent on all rotating bodies called the Coriolis force tends to make it spin, makes a vortex out of it, and what one would expect to see would be anticyclonic spin. But again, there's this problem of identifying specific features to be able to determine whether we are indeed seeing that anticyclonic vorticity. And there is some hope within the atmospheres group that by very careful study they will be able to tell us what's happening. This is the predict that the weather forecast that we looked at in real time yesterday. The prediction that the great dark spot would be here and the scooter would be here, and then the next slide shows what we all saw on the Ramtech yesterday, that indeed we were right on target with the great dark spot, and that the scooter also was about where it was supposed to be. Now, we haven't been that fortunate with all features. The secondary dark spot, the one that's at 50 or so degrees south latitude, which I just showed you, actually we missed that one, and the reason is that the prediction, of course, was made 10 days ago now, 13 days ago, and we observed its motion and tried to predict where it would be, for example, today. But in the meantime, the cloud, for reasons that we don't understand, this system, storm system, for reasons we don't understand, moved a little bit north. And when it moved a little bit north, it got into a different airstream, and it slowed down, and it's now about 20 or 30 degrees from where it was predicted to be. Unless it speeds up in a big hurry, that may mean that the other observations we are trying to get at higher and higher resolution, of course, unfortunately with smaller and smaller images against the disk of the planet, that we may miss D2 in the retargetables that are coming up. This is the prediction for today, and that's due, in fact, in, I don't know, 5 or 10 minutes or so. At the time that the frame was targeted, it was expected that this high-resolution south polar feature would be right here. But Ingersoll and his forecasters, like all forecasters, were busy making excuses for themselves this morning, and told me that, well, it was moving a little bit further ahead, and so it may actually be this far ahead. I think they're trying to cover their bets or cover themselves. But, well, in a few minutes we may have a chance to look at that and see how well they did. Going on to the ring arcs, I wanted to put together a schematic. And I apologize, it's not as clear as it could be, but and the ellipses look as though somebody sat on them. But this is the new feature that we announced yesterday, and what this diagram shows, it is a complete ring. Now there are some slight variations that are seen in its brightness, but it does go all the way around as we see it right at the moment. This is the way we see the outer arc. It has these condensations, as Ed showed you a few moments ago. One of those, we hope, will be right on the track of the Sigma-Sag occultation. And this is the main part. This is the part that we saw initially in the discovery images. But now the images that came in over the past several days or so show that there's a fainter component of that lags behind and precedes the brighter part of the arc. So it is still an arc, but it's beginning to close up. Now, the dotted lines show us where, to date anyway, we have been unable to find any material at all. I would be very surprised if there were not some material in there, and but just very little of it. Whether we will actually be able to see that before we go behind Neptune, or whether we may see it in the high phase views, that remains to be seen. But, you know, almost certainly there's material there. Whatever kind of a blocking mechanism that's keeping all this material bunched up and allowing only a small amount of it to leak out from here to here is probably not so good that it's absolutely preventing any of it from getting into this region. So I don't know what we're going to call this thing. It's probably it's a complete ring, and we may know that before the encounter is over, but it's a ring like none we've ever seen before because it's got all this material bunched up, and I guess we'll leave it up to the observers and maybe to you guys to decide what you want to call it. All right, now for an actual image, and this takes a little explaining. These are the two ring arcs. First, let me explain the artifacts in the corners and the artifacts around the bright objects. This is a star with some dark space around it. This is another star with some dark space around it. This is N3, much brighter, trailed out more than the stars because it has its own orbital motion. It was moving along during the time that the shutter was open for this image. The dark area around it, all of these are artifacts caused by using what we call a numerical filter in the processing, a digital filter. It's used to remove broad variations in the background, to kind of smooth out the background to make it a little bit easier to see what we're trying to show. And those are the continuous arc, or ring, which goes along here, the inner one, and the trailing part of the outer one. Here you see a bright part, then it dims out a little bit, little segments in here, and then maybe just barely see the extension, which goes on and eventually just fades out. So difficult to see, I can appreciate that. These are very low surface brightness features. Let's then go on to Triton, and the first image is a color image that was taken yesterday. We can see these dark and somewhat reddish regions that are up around the equatorial area. This is the bright margin, which we believe is probably the coldest part of the visible hemisphere, and then all of this mottling that you see along here. the pinkish color may be somewhat of an exaggeration. It's just very difficult on short time scales to produce color which is perfect, but the general trend is there. It is pinker than white. And if this looks slightly blue to you along this edge, that turns out not to be a contrast effect. That seems to be real, and that's particularly interesting to us. And when we say blue, let's just see what I mean by that. This is some spectrophotometric measurements that have been made recently. They put the green image at 100%. Now, the dark area, of course, is just much darker, but both of these are normalized to green. So green is 100%. And these are the dark regions, which tend to be reddish. They're red because we see a certain brightness in green light, but when you go to, say, blue, they get darker, and when you go to the ultraviolet, they get still darker. So there is that reddish color to them. If we had good red images, if we had a red filter on our cameras, it might be up here somewhere. So the dark areas are indeed red. This is that bright fringe. And here it is in green. Here it is over here in blue, slightly brighter, and over here in the UV, still brighter. Now, admittedly, there are some calibration uncertainties in the ultraviolet filter in this rather quick processing that we've tried to do. So it's difficult at this point to say if there's a real distinction between something which is just pure white or something which actually is slightly on the bluish side. If it is indeed blue, it's the only thing that's blue that we've seen on any satellite since we launched Voyager. Well, let's go on now to just the final slide. This is an image of Triton that was taken by the spacecraft at about midnight last night, and then in its 4-hour journey back to the Earth was received here at about 4 o'clock this morning. And by getting some enthusiastic people working with us in the image processing laboratory and in the photo laboratory, we were able to get this picture out and have it available to you this morning. What we're seeing is continuing higher resolution of these mottled surfaces. And what's that? Well, yeah, it's 1043, but we're looking for a narrow angle. It may be the next one up, so we can take this off for a moment, and if that narrow angle image comes in, then we can put that one up. I have hedged a little bit about whether we're really seeing the surface or whether these would be more or less stable clouds. It's getting awfully hard now to explain this away, even to some of our more conservative colleagues as atmospheric. Almost certainly we're seeing the surface, and that suggests some real excitement here Friday morning and again on Saturday morning. Now, there's still a question about what we are seeing. We're seeing bright and dark areas. The bright areas are very bright. The dark areas look dark here, but, well, I don't even want to comment on that one. I don't know. We may have to have a little chat with our forecasters. Even the areas that are dark, they look very dark on these images, but we're still talking about reflectivities up around 60 or so percent. So what are we seeing? Well, we're seeing variations in brightness. It may be controlled by topography. It may not. We'll know more about that. But what we see when we're looking at the surface of an object like Triton would be ices and then chemical modifications of the materials that make up those ices. So let's just say for the moment that the ices may be materials like nitrogen or methane. Now, when methane is bombarded by high energy particles, it gets converted into a different material, into, say, longer chain hydrocarbons. And when that happens, it changes the chemical and the physical, or may change the physical properties of this material as well. So let's imagine then that this methane gets bombarded by high energy particles, and this may happen in the atmosphere, it may happen down on the surface, and it gets darkened. If Triton did not have an atmosphere, we would just see a dark surface, perhaps not unlike some of the very dark satellites that we've seen at Uranus, and we think we are seeing in the vicinity of Neptune, well, these larger regular satellites of Neptune as well. But Triton does have an atmosphere, and with an atmosphere, the unmodified methane, and perhaps nitrogen as well, is free to migrate around. These molecules vaporize, they move around and recondense. The products, however, these photochemically changed products, may not have that freedom to do so, because by being converted chemically and now perhaps physically as well, their vapor pressures, that is their ability to get into gas form, is drastically changed. And so that stuff just kind of has to sit where it falls. And what we may be seeing here are dark areas which are made up of that chemically modified material, and bright areas, which is the unmodified methane and perhaps nitrogen as well, that is free to move around, being sublimated away from regions where the temperatures are increasing, trying to move off to a cold trap, which would be over on the other side of the satellite, not being able to condense out up here because just by virtue of being somewhat darker, these regions are absorbing more sunlight, they're staying a little bit warmer, they're a little bit too warm for condensation to take place, so that condensation may be taking place along these margins, and of course over on the other side where we can't see. So solar insolation, the warming of the ground, which can be due both to its reflectivity, its albedo, and to the slopes, will determine the distribution of this bright frost, which is able to move around on Triton's surface. And we'll have the opportunity with the high resolution images to see how much of this is due to topographical control, to local geology, and then have a better understanding of just exactly what's going on this satellite. But that's for Friday morning and Saturday morning. That's all I have at the moment.
We'll take questions now, and please wait for the microphone. Dave Perlman. We'll get you another mic, Dave. Greg? Steve? Do we have any more mics? Booth?
Test. Hello? Yeah.
Hey!
Well, it was a question for Brad Smith on the diagram of the globe showing the circular aspect of the one ring we know is a ring and the other material which may or may not be a ring. What is can you give us in degrees the location of those rings? They don't appear to be precisely equatorial by any means. What kind of angle is involved there?
Yeah, I apologize for that artwork. It did not come out the way we had intended it to. They are equatorial. They are in the plane of the planet's equator. And they are circular as closely as we can measure them.
Marguerite?
Hi, this is also a question for Brad Smith. Brad, when you were showing us the smaller dark spot that has the light material in it that was changing over a period of time, you were talking about what kind of time frame for those changes?
This was the atmospheric dark spot with the white. Those images, 6 or 7 of them, were taken on successive rotations as we define the rotation period, so they are approximately 18 hours apart.
Yes, right over here.
Yeah, Tom Elias, Scripps Howard newspapers. In describing what you saw on Triton, Dr. Smith, you said that the blue area, or apparently blue area, is the only thing blue that you've seen on any satellite since launching Voyager. If indeed you are seeing blue, or we are seeing blue, is there any idea what's making it blue, and why there's nothing similar on any of the other satellites?
Well, we had a discussion last night. We have an explanation. We don't know if it's a good explanation, but an explanation. This is kind of stream of consciousness thinking now. You know, we just really haven't had a chance to do a careful analysis. You know that gas molecules preferentially scatter radiation, that is light, in that they scatter more efficiently at shorter wavelengths, and that's what makes our sky blue. Right? That's what produces a blue sky. Turns out that to some extent, very, very small solid particles do the same thing, so that if you get extremely small particles, much smaller than the wavelength of light, they can also have scattering properties which are similar to Rayleigh scattering, that is, wavelength-dependent scattering. We suspect that gas, probably methane, maybe nitrogen, is migrating poleward, that is, toward the north, and recondensing in this cold region. And if in its condensation and forming crystals on the surface, these crystals are extremely small, submicron, down in a few tenths of a micron perhaps. They could scatter light in a sort of a Rayleigh scattering mechanism, and would tend to look somewhat bluish. That may not be the right explanation. It's the only explanation that we've been able to come up with so far, because we just don't know of any materials that would be naturally blue that we would expect to see on Triton.
Linda?
Linda Doran of the San Gabriel Valley Tribune. I have a question for Norm Haynes. Could you explain in layman's terms why it was necessary to get completely out of view of the sun as well as out of view of the Earth?
You're talking about the dual occultation zones. It's actually a science reason. We have the Earth occultation experiment is to allow the radio beam from the spacecraft to go through the atmosphere before it goes behind the planet, and the radio beam is affected by the planet, or by the atmosphere of the satellite. And by looking at the signature of that radio signal, you can tell what's in the atmosphere. There's also another instrument on board the spacecraft that looks at the sun, and as the sun sets behind the target planet, you can tell what's in the atmosphere by looking at how the atmosphere absorbs features out of the sunlight. There's two different ways of doing the experiment. We want to do both.
Lee Siegel, over here.
Hi, Dr. Stone and Dr. Smith, could you each tell me your opinion of the possibility, I understand it's been discussed by some people in the science teams, that the darker areas on Triton, or at least one of them seen on a view that was on the screen about 6 a.m. this morning, is an impact crater?
We're seeing Triton at a relatively low phase angle right now. I don't recall exactly what it is, 20 degrees or thereabouts. That's like seeing the moon just a few days before full. It's not the kind of lighting that you would like to have to detect topographic features, because they are generally detected by their shadowing. So we are seeing only albedo effects. Now, when you see a bright circle on the moon, you would just naturally believe that you were seeing a crater that when the lighting got better would show its true topography. It's a little bit more dangerous to assume that when you're seeing a bright circle on Triton that you're seeing craters. We don't know what the geological history of Triton is. Certainly it's been bombarded. It could never have escaped that. But the surface is very close to the melting point of its own material. Craters can relax, they can disappear, volatiles are moving around, they could be covered up. I think it's an open question as to whether we will see large impacts and impact craters. And if you're seeing something that's circular right at the moment, I would say that your guess right at the moment would be every bit as good as any that we could make. It's possible, but not certain.
Yes, over here, Jonathan.
Dr. Stone, speaking, I believe, of the PRA data, you said there's, quote, no question at all the emission is coming from Neptune, unquote. Is there still, what are the possibilities for the role of Triton in the electromagnetic signature of the Neptune system?
Well, I think the radio emission is coming from Neptune's magnetic field. All right, so I think that's a fair statement. So it is coming from Neptune, not from Triton. I think that I think they have not pursued in any more detail this issue of whether Triton is providing any control or not, partly because in another, perhaps by midnight tonight, we're going to have the answer. So the point is, you only spend so much time speculating before you just get on with your business.
The next gentleman over.
Govert Schilling, working for Dutch magazines. The fact that this southern dark spot has moved to a northern latitude, does that suggest to you that it origins in a deeper layer of the atmosphere, or would there be a mechanism that it could move to another latitude in the upper parts of the atmosphere?
I think that almost anything that we see at the higher levels where the visible clouds are represent the upper level of some system that goes very much deeper into the atmosphere. And so its motion, its drifting north or south, may well be controlled by currents that we have no visibility into at all that are deeper. It doesn't have to move very far, by the way. Just a small shift in latitude is enough to put it into a different wind stream up at the upper level, and at least take the top of that feature and move it at a different rate. And then the accumulated difference now has built up to something like 20 degrees or so. Detected, no, because you can't see down, but modeled, yes. The Great Red Spot, for example, undoubtedly has its roots, its convective roots at... yes. So.
Yes, over here.
Cooper, Pioneer Productions, London. Yesterday you did a lot of ultraviolet investigations into the possibility of finding the aurora australis. What results did you get?
Well, the report this morning was that they did acquire the data, and they're in the process of looking at it very carefully. I'm hoping that sometime later today we'll hear the results of that. Perhaps we'll have some results to report tomorrow. But it does take time to analyze the data. But the data was successfully acquired.
Yes, over here.
This is Akira Hasegawa of Bell Laboratories and Asahi Television Japan. This is a question to Brad. Yesterday you reported that the altitude of the dark spot was lower than the rest, which tends to indicate that it is a low pressure area rather than high pressure area. And then it seems to me that if it is a cyclone, it will be rotating in the cyclone direction instead of anti-cyclone direction. Do you have any comment on that? I'd like to add one more question about this white cloud that we see on the surface of Neptune. I recall that we did not see similar cloud activity in other planets like Jupiter and Saturn. And if that is the case,
In that case, what is unique about Neptune? Yeah. What I said was that the great dark spot was lower than these wispy cirrus-type clouds. I didn't say, nor do we know, its height relative to its surrounding clouds. So at that point, it's not really telling us anything as to whether it's high pressure or low pressure, cyclonic or anticyclonic. These white clouds are up at a very high altitude, and I don't think that there is that we have seen corresponding or similar features in other planets. Now, we have seen white clouds in Jupiter's atmosphere. We've seen them in Saturn's atmosphere, but they have different morphology. These are long, drawn-out, wispy types of features which are morphologically similar to cirrus-type clouds in our atmosphere, and they are the highest, except for certain non-volatile, noctilucent clouds. They are the highest clouds that we have in our atmosphere, and they may well be the highest clouds that we have in the Neptune atmosphere, and they may not be telling us very much about what's happening at the next level down where everything else seems to be.
Carlos?
Byers, Houston Chronicle. Brad, to follow on the upper level cloud question, earlier you had told us, I believe, that these might be H2S. Have you got any other information that would confirm that, indicate differently what the nature of the clouds is?
I certainly don't recall saying H2S. Is that?
I think I was the one who pointed out that there are probably two cloud decks, the top cloud deck likely being methane, and the deeper cloud deck maybe being hydrogen sulfide. But we have no direct indication that that is what that cloud is, either from ground-based or from Voyager. It's a supposition based on a theoretical model.
But the methane is perhaps a little easier to identify because we know that the atmosphere is rich in methane and it condenses out at some level.
We know there's methane in the atmosphere.
That looks like noise. It looks like the signal's a bit noisy.
Trudy?
Yeah, it's noise.
If I recall correctly, you had said that I'm Trudy Bell from IEEE Spectrum. If I recall correctly, you had said that the radio emissions had a periodicity of about 16 hours.
Yes.
If I recall correctly, the scooter also has a periodicity of about 16 hours.
Yes.
Could there be any possible connection between a magnetic field of a planet and an atmospheric feature?
Well, I don't think that there's a direct connection in the sense that there's a mechanical connection or anything, but if the 16-hour periodicity is really the rotation rate of the interior of the planet, then it might not be unreasonable to find some features on the planet which have that same rate of rotation. But obviously there are winds, and so there are very large differences in the rates at which various features move.
However, what would be strange is the situation that we have yet to have not encountered so far is to have the very fastest clouds having the rotation of the interior part and everything else that we've been able to find in the atmosphere moving more slowly. That says that all winds are easterly, and that's a strange situation.
Joel?
Joel Davis, freelance. Ed, you talked about the plasma wave instrument has now detected emissions.
Yes.
Do we now have, or do we yet have, any periodicity to those emissions, and if so, what is it?
No, it's just been detected, and it's still too early. They've just come up above their threshold, basically, because they're at much lower frequency. And so it's a little early yet to sort it out. As you may remember, radio emissions, in fact, are very complex in their frequency content. And so they're being very cautious and making sure that they're understanding exactly what they're seeing. And so I hope, again, by tomorrow, when the signals are going to be much stronger, that they'll have a much better story put together.
Is that mic working over there? Yes. John?
Yeah, I can hear you.
Are there any mechanisms that would separate chunkier, darker material in a ring from finer material in a ring at the same radius? Are you thinking about how you could get this kind of clumping, or if you have different materials, would they tend to mix evenly?
Well, I think it is true the shepherding mechanism works best for particles which are of some size, and probably does not work well for really fine dust material. So there is a reason why one might be able to confine the larger pieces, but not the fine dust, for instance. But as far as other mechanisms to provide the clumpiness, I think, again, as we discussed yesterday, one really needs to know what other satellites are in that region. That, I think, is the first order question, and hopefully that analysis will be completed, and one will know if there are any other major satellites which might be causing some of the structure. But they have no answers now. There are no answers.
In the last row over here.
Stephen Strauss, the Globe and Mail. I have two questions. First, if we're standing on Triton in the blue area, do we look down and see blue ground? Do we look up and see blue sky? The second question is, the growing white area in the southern dark spot, if it is convection, is it going to be telling us something about materials lower down in the planet's atmosphere?
Well, just to go to the first part of your question. We don't know what the atmospheric pressure is on Triton. It might be size 10 millibars. It might be less than a millibar. I would imagine that if you were standing on Triton, the sky would look pretty black to you, although off toward the horizon you might see a bluish glow. If you look down at your feet, well, as I mentioned, this hypothesis really represents just some free thinking that was done last night, because we couldn't come up with another explanation. But if you look down at your feet, you would see something that was primarily bright, but might be on the bluish side of bright. And the second part wasn't terribly clear. You were asking if higher resolution analysis of this area would tell what?
If we have an upwelling of things further down, which is what I was understanding the white clouds were suggesting, does this mean we're going to get a view of what is the composition further down from those
We're talking
clouds?
about Neptune now.
That's
The
right.
upwelling
From
of
Neptune,
Neptune.
yes,
Yeah. Well, our belief is these whitish clouds are methane, and so methane is mixed well within the atmosphere. It may be very similar to the Earth, maybe not perfectly mixed everywhere, but it appears throughout the atmosphere. And if this is convective upwelling, then when that methane reaches a level of condensation, as water does in our atmosphere, it freezes out and produces ice crystals. I don't think that tells us any more than what I've just said. It doesn't identify other species or really tell us what's happening down below.
We have a question from the other press side here at JPL.
Yes, it's Lee Palmer from British Columbia Knowledge Network. I have a two-part question for Brad Smith. The first question, Heidi Hamill is simultaneously imaging Neptune in the methane bands from Hawaii. I'd like to know which telescope she's using. And my second question deals with the images of Triton. Does the imaging team have software which is capable of correlating or cross-correlating images of Triton taken at different times, say an hour apart, to determine perhaps if some features are real and not in the surface features and not in the atmosphere?
The answer to your first question is Heidi Hamill is using the 88-inch telescope on Mauna Kea. The cross-correlation, we have the software to map project. We can, in fact, measure a latitude and longitude of every feature that we see. That doesn't fully answer the question. We have recognized for quite some time now that what we're seeing is relatively fixed, or can be quite precisely fixed in this coordinate system for this satellite. What we can't tell, or have not been able to tell, it's just our impression now that we are seeing the surface, is whether or not the albedo features we were seeing were actually on the surface or whether they were clouds which were topographically controlled, that is, hollows in which ground fog was forming, or what is sometimes called lee wave clouds over a mountain. They tend to be fixed with respect to the topography. And in being cautious, we could not rule out the possibility that we were seeing those. However, just from its appearance, it just looks more and more every day now that this is indeed the surface we're seeing.
Kelly Beatty.
Kelly Beatty, Sky and Telescope. Brad, do I understand that one of the, in your current thinking, one of the Earth occultations corresponds to 1989 and 2, and therefore Voyager is confirming Reitzma's observation of the satellite?
To me, as improbable an event that would have been for somebody watching an occultation from the Earth and just having one of these little satellites go in front of the star, a very improbable event. It does really seem that that's what happened. The event, which was recorded by two telescopes a few hundred meters apart in Tucson, were very deep events. In other words, they were indistinguishable from complete opacity, infinite optical thickness. And we don't see any part of the ring system that would suggest that the rings are of infinite optical thickness. That leads us to the conclusion that they just observed something which must be a chance in thousands or something like that. Let's see. I think Harold Reitzma and
Bill Hubbard.
And Bill Hubbard, yeah.
Bob Cowan.
Christian Science Monitor. We heard on the earlier TV report that Voyager was going to arrive 4 minutes, 45 seconds earlier than planned. Could you comment on that, and does that change the pass distance at Neptune and Triton?
No, the arrival time doesn't change the pass distance. In other words, the spot we aimed at Neptune is, we know, within 33 kilometers or thereabouts. And we now know the time of arrival, even though it's earlier than we'd originally thought. We now know that time to within a couple of seconds. And we've been able to accommodate that time shift in the sequences that are on the spacecraft. So we've essentially slid all the observations by that amount of time so that they take place at the proper time before closest approach. Minutes. In fact, I don't have with me this morning the precise time. I've got the uncertainty, but not the time. I can get that for you if you wish. It's close to that.
Mark Washburn.
Mark Washburn, Air and Space. In the Triton sequence that came down this morning, the last picture in the run was in a UV filter, and it looked quite different. Could you just describe what it is we're likely to see in the UV filter as opposed to the clear filter? I mean, is it more likely to show us ice or clouds or what?
The highest contrast that we see up until now has been actually through the violet filter. The UV contrasts and the clear contrasts are both slightly lower. The image that I showed you this morning was clear, and you may have noticed it wasn't quite as contrasty as the one I showed yesterday morning, and that's because the violet image was somewhat smeared, and we elected to go with the clear one instead. But a UV image or a violet image or a green image in itself doesn't tell us anything. It's when we compare them that we have color, and that's the value of these different filters.
On this aisle, right over here.
George McQuaid, KGIL News Talk Radio, Los Angeles. You mentioned midnight. Is that the peak viewing time, and what are you hoping to see? Maybe all three could answer.
Well, the midnight prediction I made had to do with the possible, that's an approximate time when one might expect to detect the bow shock out in front of the magnetosphere. There will be no images. That's strictly a shock in the solar wind itself, which will be detectable with the other instruments. So there will be no image of that. I think the images which will be coming down, which I showed on the view graph around midnight, starting at what 9 p.m. That's the map we're making, the infrared map that we're making of the planet around midnight.
So after that, is there a peak time that you're looking for, and what impact will the cloud formation have? What impact will the cloud formation have on your viewing tomorrow?
What cloud formation?
You were talking about the cyclonic motions earlier. Is that going to affect your viewing?
Well, does the bow shock affect our viewing? No. We continue with our sequence, which is to re-target and re-image these atmospheric features that we selected a couple of weeks ago, and that just continues.
Lee Siegel.
Brad, two quick question and a longer one. Are any of your suspects here and there in the way of moons that you mentioned yesterday been firmed up yet? Are you ready to say that any of them are yet? You're convinced there are more moons? And the second question is, I may be wrong on this, but my recollection is that during the Uranus encounter, there was less announced in terms of discoveries in the month or so before your daily news conferences started than this time, but more announced by now since the news conferences started. Is that a function of what the spacecraft's doing, some difference in that, or I'm just wondering, or is it just a quirk?
We started earlier because we were learning things earlier. Neptune was so poorly observed from the Earth that even last spring we were seeing things for the first time, the great dark spot, for example. So we paced things out a little bit differently with Neptune than we have for earlier encounters. With regard to the satellites, I am absolutely convinced that there are other satellites. It is, just as I mentioned earlier, a low priority for us now. We have other things. The images are there. They will be analyzed. As time becomes available and we can stop worrying about knowing exactly where the ring arc segments are going to be and so on, then the people who do this in the navigation area, who actually compute the ephemerides for these satellites, will get that work done, and they'll be released. The policy in general is that in order to release information on a satellite, you do it with all of the information that's required, its orbital period, its distance from Neptune, and so forth. And that will be forthcoming.
So you're not willing to say there's X number of expected new moons right
I
now.
didn't say exactly that. There's X numbers of new moons.
Bill Harwood?
No, I've just lost track. Maybe two, maybe more. I just don't have the information.
Bill, in the back.
Bill Harwood, UPI. For Norm, would you expand a little bit on the 951 load that goes up today? Give us a little idea of the kind of work that went into refining that. And I was looking to get a feel for how big that thing is in terms of what kind of, would it fit in my pocket calculator, for example, if you could put that in more everyday terms.
Okay. It turns out the spacecraft is operated by, the spacecraft sequences are run out of a computer on board. So what we do is we load a program in, and the program then executes all the various steps that the spacecraft has to go through to take all the observations and send all the data back. Our computer on board that we use for this has only got a couple of thousand words of memory available for what we call sequencing. So when we have sequences that are not real complicated, we can put that on board the spacecraft, and there's enough space there to operate the spacecraft for perhaps days or weeks. For example, Voyager 1 is operating on a 6-month sequence. But when we get very close to an encounter, for example, we're very close to Neptune, the sequences are very complex. The spacecraft is essentially doing something all the time. It's moving the platform, recording data, playing data back. So those sequences only last a very short period of time. We don't have room on the spacecraft to put more than a couple, 2 or 3 days worth of data into the computer. And what we're sending up this afternoon is the sequence load which will take over the operation of the spacecraft tomorrow and run it for on the order of 2 to 2.5 days. It will take it through the closest approach with Neptune and Triton. Then at that point in time, we'll have to send up another computer load to pick the spacecraft up at that point and carry it on for several more days. So it's been a repetitive process, something we've had to do all along ever since launch, and when you get close to encounter, we have to do it very often and very frequently. Now the load that we're sending up is a complex load, and it's also what's in that complex load are a lot of moving the scan platform to look at the various objects, and the pointing directions and the timing of these observations are critically dependent on what the actual trajectory is. So as we get a better and better knowledge and better handle on what the real trajectory is, we have to go back in and continually refine those little pointing directions and timing. And in fact, we'll send the command load up this afternoon, but tomorrow we'll have one last opportunity to actually tweak a few of the parameters after they've gone into the spacecraft. The last minute changes with the very best estimate that we've got of the actual trajectory past both Neptune and Triton. Whether it fit in your pocket calculator, I'm not sure how many words your pocket calculator has, but if it's got more than 2,000 words, it would fit.
We have another question from the remote site here at JPL.
David Seidel, World Space Foundation, for Ed. When the Voyagers encountered the strong Jovian field, they crossed the bow shock several times. Now the Neptune system is much weaker, but with the active sun, do you expect to have multiple bow shock crossings? And is Voyager 1 being used to collect any data to support the particles and fields environment out in deep space?
The number of bow shock encounters really depends on how variable the solar wind is, and if the solar wind gusts, then of course the magnetosphere can breathe in and out. It appears as though we're in a very quiescent wind condition, so I suspect multiple bow shock crossings won't happen. In terms of use of Voyager 1, the problem is that Voyager 1 is now some 20 astronomical units, where the Earth is 1 from the Sun. The Voyager is 20 of those astronomical units above the plane of the planets, and the solar wind at that latitude is markedly different than what's observed in the plane of the planets, and so it does not provide very useful predictive capability. We're using Pioneer 11, which is closer to the plane of the planets, however, to provide some predictive information, and that prediction is that we should see a very quiet wind.
The lady in the back over here.
Another small question for Norman Haynes. What is the last figure you announced for the height at which Voyager 2 will pass above the clouds of Neptune? And for Brad Smith, will you have the possibility of completing the ring, which is not already completed, with the pictures you've already done, or have you sent orders to do that? And when you say that the so-called cirrus above the planet are high above the planet, what is the estimate distance?
The distance of closest approach above the clouds, I don't have the actual detailed figures with me, but it's very close to our nominal point, which was about 5,000 kilometers, or on the order of 3,000 miles. If you like, I'll get you the actual figures later.
With regard to the heights of the clouds, I hope that over the next 2 days or so, we will be able to give some estimates as to the relative heights of these clouds. The cirrus-type clouds, the great dark spot, perhaps some other features. So there's some belief that we can do that within the team, that we can do that in the next few days. And you have one more question that the ring, yeah. In the images that we have right at the moment, which have not been given the very best processing they could, but still quite good, we are not able to see that outer ring arc all the way around. I am not certain whether there are any images that will be taken before encounter that will help us out, but possibly the post-encounter images that are taken at a relatively high phase angle may give us the information we need there.
David Dow.
David Dow, CBS News. You mentioned at the beginning of this conference that scientists were literally, your team was literally jumping up and down as the pictures came down. Remembering the excitement that Io created at Jupiter, at times almost overshadowing the findings at Jupiter, and noting the mystery that surrounds Triton as you approach it, is there on your team any sense of anticipation that they may be coming on another Io, not necessarily in terms of volcanic activity, but in terms of its uniqueness and diversity?
Certainly. We're looking at a satellite right now which has some interesting structure in these relatively low resolution frames. We know what the resolution is going to be on Friday morning, and even higher on Saturday morning. I would say that there's an enormous sense of anticipation on the part of the whole team. Not just the people who are interested in satellites. You know, everybody will be looking at those images because we have absolutely no idea what we're going to see.
Yes, over here, please.
Nigel Henbest, New Scientist. Some of the very early pictures of Neptune going back about 6 months showed a large white feature, which, first of all, is that what we're now calling cirrus? And secondly, is that related to any of the features we're seeing now, for example, the Great Dark Spot?
Yeah, it's the same thing. They're the same features that have been seen from the ground. They are methane condensed methane, very, very high in the planet's atmosphere, and they show up. They are the only features that we have been able to see from the ground, and we've been able to see them in the Voyager images since I think last January.
Any other feature that we can see now?
Say again?
I'm sorry, is that actually topographically over the Great Dark Spot? Is it actually related
They
to it?
they are certainly higher. Those that are in the vicinity of the Great Dark Spot are certainly higher than the Great Dark Spot. There's no question about that. On the other hand, there is another feature which we know is very low. It's bright, but we know is very low and would not have been seen in the ground-based images.
Kevin?
Kevin Langdon, Santa Barbara News Press. And looking at the images that you put up on the screen of Triton, we don't see quite as much as we see later when the photos are released. So I'm speaking in relation to yesterday's black and white Triton image. I was really struck by two things on that image. One of them is the concentric circles at the lower left, which seem to cross some of the light-dark boundaries. And the other one is that there are some irregularly shaped features, particularly one large one where the boundary looks sort of like an inverted question mark, where there seemed to be a dark band around the outside of the light area and following that, the same configuration. It was quite striking that the parallel curved lines there and in a couple of other places. Can you say something about what you think that might be?
Well, we cannot answer that. There are features, I agree. I hadn't seen it in the image yesterday, but when I looked at the hard copy, I saw a circular feature. It's visible in today's images. It's just moved over a little bit, rotated over a little bit. There are a number of things that it might be. Certainly an impact crater is a possibility. There are other things that produce more or less circular type features. This whole surface of Triton may be analogous to a sort of a permafrost, tundra type geology with material very close to its melting point. It's just, there are so many possibilities that, and those things will sometimes produce circular features. There are so many possibilities that we just simply, we can't make any decision now. We need to see the topography. We need to see the geology. That will not happen until we get the high-resolution images on Friday morning and Saturday morning.
I think one thing that makes it so puzzling or so difficult to understand is the fact that unlike the other icy moons, which have water ice on their surface, which is quite hard at these temperatures, methane ice and nitrogen ice, if it's there, is quite soft and will flow, just like a glacier. So in fact, that further complicates any anticipation as to what these things might be, because this ice is not rigid ice like the water ice that we've seen on other satellites. So I think I agree with Brad. Everybody is anticipating. Well, when you look at the thing, it clearly doesn't look like anything we've seen before, even though it's very low resolution. That gives us some more than a little hope that it will, in fact, be quite different than anything we've seen before. And yes, there's a lot of anticipation.
Yes, in the far back on the other side.
And Andrew Yee, Science North. Has the imaging team obtained accurate figures on the rotation rate, color, albedo, and size of Nereid?
Yeah, I had hoped to be able to say something about that today. The people who do that sort of work, who are looking at the images, trying to measure the width of the image, comparing it with star images, trying to tell us something about variability and so on, they have been putting their time into studying 1979 N1 and 1989 N1 and 89, I lost 10 years, 89 N2, because we are going to be seeing these satellites at very high resolution. So we had to put a lot of work into them to try to guess what the albedos were so we could set the right exposure times and so forth. Nereid, because we will not see it up close, has been given lower priority. But I understand there's an interest in it. I will try to get that information, and I will try to have it here tomorrow. What do we know about Nereid? Is it varying in brightness? How big is it? And so forth. And so if the team is hearing this, go to work on it.
Glenda?
How much do you expect the resolution to improve by the time you get to the closest encounter with Triton? Will it be a factor of 5 times better, or can you estimate from the images you have, let's say yesterday and today?
Than what we're seeing right now?
Yeah.
Oh, well, way
You're
more
saying you're
than
going to
that.
get much higher resolutions. I mean, how much higher?
Yeah, exactly how high the resolution will be will depend somewhat on how well we compensate for smear, but it seems to me that we'll be down in the few kilometers, and we're up around 30, 20 right now, so we're talking about a factor of 10, not 5.
Yes, Dutch publications.
Is the orbit of 1989 N2 known well enough to calculate whether it was on the right position during the Earth occultation? And if not, will that be the case after your detailed observations of this moon?
I would, this is just, I'm not a celestial mechanician. This is just a guess that when the orbit is pinned down well enough that it could be worked backward in time. That occultation did not include Neptune, so from the ground we don't know exactly where it was, but it seems as though 79 N2 has to be the object that was there, and one in fact could turn the problem around if within some limits we might be able to say where N2 was at that time.
Trudy?
Just when you had mentioned glaciers, it suggested something. I mean, one well-known phenomenon in glaciers on the Earth is that because of the tremendous pressures that the material is under, you get a bluish cast, which has to do with the way the water is, or the air is compressed, as I gather, in the glacier. With the materials that are on Triton, could there possibly be a similar type of phenomenon where you could, I mean, knowing what little is known at this point about what might be there, is there any possibility that a bluish cast might come from some similar kind of mechanism on Triton?
Yeah, the bluishness in glaciers due, my understanding, is a selective absorption by red light by water. We're dealing here with methane, and I suppose that's a possibility. I don't know what the color of thick slabs of methane would be.
Mark?
Let me just try again on the question I asked earlier. Maybe I put it badly. Okay. You have a clear filter shot of Triton followed by a UV filter shot.
Yep.
In the UV, there's some bright stuff that wasn't as apparent in the clear. What does it imply about the nature of the bright stuff that we see it in UV but not in the clear?
Okay, you're referring to some specific images that, in that case, you have a disadvantage on me because this morning I was preparing for this and didn't have a chance to look at any.
So was I.
On this aisle.
Jim Tranquata with the Los Angeles Daily News, a question for Norm Haynes. Could you discuss the element of risk involved during the close encounter period with radiation and the magnetic pull of the planet and the possible effect that would have on Voyager?
I'll start and then I'll let Ed finish, perhaps. We, some time ago, a couple of years ago or more, had some experts get together and develop what they thought would be the nominal and perhaps the worst case magnetic field and therefore the worst case radiation belt that we might have to traverse. And that was all taken into account when we designed the mission. Based on those particular models, we don't believe there's a great element of risk. If we encountered the worst of those radiation fields, we might have experienced a few glitches in one of our computer clocks, but we've also added some software into the spacecraft to help compensate for those if they do occur. If the question then is, do we think that we're going to encounter anything different than we anticipated in those models? I don't think so, but I'm going to let Ed answer that one.
Well, obviously, until we get there, we don't know what's there. So that's say that right up front. But we certainly have Voyager 1 flew by Jupiter, which is known to have a very intense radiation environment of very high energy electrons, and we survived that quite well. We did have some timing shifts, and we've learned how to take those into account so that they won't bother us. And so I think we're prepared, even if it's as intense as Jupiter, which would, I think, be a big surprise for everyone.
Down here on the center aisle.
Tom Siegfried, Dallas Morning News. I just wondered on the image of the rings you showed where it appears very faintly, what was the exposure time to get even that much of an image?
I think that was approximately a 1 minute exposure, I believe. I can check on that. And, Pardon? 61 seconds. That's close to a minute.
Close to a minute.
Are there any more questions? On the other side.
Sean Sullivan, freelance. I was wondering about the occultation that's been interpreted as 1989 N2. There was some discussion yesterday of a possible moonlit belt that might be the source material for the ring arcs. Could this occultation have been from a couple of kilometer-sized moon in a belt like that would increase the probability of hitting something?
I'm sorry, I didn't quite understand.
Could it be a moon that was a few kilometer-sized moon embedded in a belt? Was that your question?
Could there be a belt of moons too small to resolve presently with the cameras, but larger than ring particle size? Could this have been a small object like that? That would have been was there a minimum size set by the occultation observation?
No. In fact, there is a measured size, and the uncertainty is whether it was a retrograde or a prograde moving object. But if you assume that it was caused by a satellite moving through in front of the star, then the duration of that event is consistent with the size of 1989 N2.
Thank you.
afternoon, and welcome again to Voyager Update. I'm Al Hibbs. At 12 o'clock noon Pacific Daylight Time, the Voyager spacecraft is 2,061,000 kilometers above the cloud top. That works out to 1,272,000 miles, and it's heading for Neptune now at 37,890 miles per hour. Right now we are entering a period which is dominated by infrared observations. At the present time, the spacecraft is calibrating its infrared spectrometer by looking out into empty space. This goes on for about almost 20 minutes. And then starting at 10 after 12, the infrared observations are going to go back on the planet. They'll be going to make temperature measurements and around the high southern latitudes, and along with the infrared observations, supporting those will be photopolarimeter and ultraviolet spectrometer observations. So those will go on for a couple of hours, but we'll be back at 1 o'clock with the next update. I'm Al Hibbs.
We were surprised. We expected this body to be rather like the moon.
This was quite an interesting discovery. It was one that we thought we might find.
Command Center for the Deep Space Mission, which in the past few days has carried the eyes of man farther than they've ever been.
And the science is pushed in amazing.
Just last
like
night,
fitting a jigsaw puzzle
we
together.
had these frames come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour. Good afternoon. Welcome to the 1 o'clock edition of Voyager Update. I'm Al Hibbs, and at 1 p.m. Pacific Daylight Time, the Voyager spacecraft is 1,986,000 kilometers, or that works out to 1,234,000 miles above the cloud tops of Neptune and speeding toward the planet at 37,903 miles per hour. We have with us this afternoon William Farrell of the Planetary Radio Astronomy team. And Bill, when Warwick was talking at the press conference, I think it was Monday, he said that he was seeing something that looked very much like a 16-hour period in the signals that he was getting in the Planetary Radio Astronomy instrument, which he distrusted because that's 16 hours and 24 hours are sort of in synchrony with each other. It might be an Earth rotation effect. How do we stand on that?
Well, actually, that's a very interesting point. What's happened is that 16-hour period was based on one particular radio mission, these bursts that were observed between about 600 kilohertz and 1,200 kilohertz. Well, since then, there's a new radio emission that's been seen, a smooth component that also has this a very similar 16.2-hour periodicity that was determined by Alan Lekashow and the people at Medan Observatory, who are also PRA investigators. Right. So it's a very interesting turn, because we now have 2 radio emissions to work with from this planet.
So the one that Warwick first saw was just a sharp burst that lasted very briefly. And
Yes,
this is
sir,
sort of
right.
a long-term buzz at a lower frequency that goes on for hours.
That's right. At this point, the events, the smooth emission seems to last for about 6 to 8 hours. And to make things a little bit more complicated and more interesting, it also seems to have some polarization reversals also associated with it, which will make it, we're not quite sure what to make of that yet, but it adds to the fun.
Does that imply 2 different sources that we're looking at?
Or maybe one source with different beaming. Too early to say really what's happening with that. Right?
Is it exactly 16 hours, or
No,
do we have
it's-
some decimal points?
Yeah, there is some decimal points. The 16.2 hours is what Alan Lekashow. 16.2, right? Plus or minus, I believe, 0.2. But don't hold me to that. Okay. Right, and I believe the bursting mission has roughly the same periodicity, although maybe a little different. Right, and that's something we're looking into now, how they might differ in periodicity.
How does a planet generate radio waves that you detect?
Well, that's a good question. Actually, at Earth and at Jupiter and Saturn seems to be roughly the same effect. What's happening is energetic electrons travel down a magnetic field line, and as they travel down, they spiral, and these spiraling particles radiate their radiation, and in the end, they end up depositing into the upper atmosphere, like in the case of the Earth, forming the very discrete northern aurora borealis, northern lights.
So the source of the radio waves then is high above the atmosphere of the planet.
Oh, that's right. Maybe kind of a standard working unit is 1.2 to 1.4 planetary radii. Yeah, it varies from planet to planet, but that's for these cyclotron-related emissions. That's kind of a working figure that's used. This is very general, though. Right?
So the electrons spiral down around the magnetic lines and are being carried by the magnetic lines as the planet rotates.
Yes, that's right.
So what we're really looking at is the period of rotation of the magnetic field.
That's, I don't want to neither confirm or deny that. You know,
But I mean, that's...
being from Washington, that's that's a standard answer. But I should be careful. But anyway, yeah. But we'll just say now it's a 16-hour periodicity, and we've seen it in two radio missions.
So the relationship between this and the planet itself is the relationship of the magnetic field to the central core, which presumably is generating the magnetic
That's right.
field.
That's right. Right.
So if this is the period we're seeing is real, it's the period at which the center core of Neptune is rotating.
Yeah, hopefully, right.
Yeah.
Right. But again, it's still early and you know, right, to say that completely. But it's 16-hour occurrence period, right?
Generated by electrons in the magnetic field above the atmosphere.
That's right. That's right. And hopefully, well, you know, as of lunch today, talking to some of the investigators at the ultraviolet group, UVS group, they haven't seen a signature of these deposited electrons. They should deposit themselves and make a bright
aurora someplace.
That's right. That's right. And but they haven't seen a signature yet. But it's still the slit their slit still is
still has a very wide field of view for the ultraviolet. When that narrows down, they might be able to see it.
That's right. That's right.
That would be really marvelous.
Right. To have both. Right. Right. But.
Yeah. Well, thank you. Thank you very much, Bill.
Well, very good. Thank you. Right.
For having me with us, and we'll be back in another hour. So until 2 o'clock this afternoon, this is Voyager Update.
No, we were surprised. We expected this body to be rather like the moon.
This was quite an interesting discovery. It was one that we thought we might find.
Command Center for the Deep Space Mission, which in the past few days has carried the eyes of men farther than they've ever been.
And the science is pushed in amazing.
Just
It's
last
like
night,
fitting a jigsaw puzzle
we
together.
had these frames come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour. Good afternoon. Welcome to the 2 o'clock edition of Voyager Update. I'm Al Hibbs, and at 2 o'clock p.m. Pacific Daylight Time, the Voyager is 1,939,000 kilometers, or 1,197,000 miles above the cloud tops of Neptune, and is heading toward the planet at 37,918 miles per hour. And if you've been keeping track of these numbers, you know it's speeding up constantly. On any trip that you might take, there are bound to be a few rose hazards or environmental factors you might want to take into consideration when planning a long journey. And with me now to discuss the road hazards that Voyager might encounter on its tour of the Neptune system, Rex Ridenour of the Voyager project team. Welcome, Rex. I take it thinking about what might damage the spacecraft as we go past Neptune has occupied quite a bit of your time lately.
Yeah, about the last 3 years, I've been working off and on most of that time trying to keep track of our models that various people on lab are generating for the rings, the radiation, the atmosphere, because we know we're going close to all those.
Yeah,
we have for quite a few years, and the idea is to keep track of the models and then try to figure out what those models are telling us about a possible hazard. And
well, why don't you step us through the track and tell us what we're likely to run into.
we've got several ways to demonstrate that.
All right.
The first thing here is just to get oriented. This whole discussion only involves about plus or minus 2 hours around Neptune closest approach, which is roughly the time frame shown on this figure. And Voyager 2 comes in from the right, goes over the top of Neptune, and then down. We get an arrow up here. We can see that the first thing we run into, if you look at the geometry here, is what we've modeled as the Van Allen radiation belts, essentially, around Neptune. And this is all a model. It looks like we might be close based on the most recent data. The orientation is roughly what we've modeled, which is aligned with the pole, like this, of the magnetic field.
Magnetic field is more or less aligned with the spin axis.
Yeah, so, you know, plus or minus 10 degrees or so, we'll get some radiation belts, something like this. As we go past through that peak of intensity there, we shortly thereafter cross the ring plane, which goes where this arrow is going here. And we're very close to the outer edge of the ring system. I guess we can call it rings or ring arcs now.
Whatever, but at least the ones we know about.
Right, and that's about an hour before closest approach, which comes up right here. And then only about 10 minutes around closest approach, we have a hazard we've looked at in detail for the atmosphere, because we are very close relatively to the clouds. And above the clouds is a diffuse layer of whatever, you know, ions or whatever. So we had to look at that. And for each one of these hazards, we've actually done some things in the sequence to try to bulletproof everything to make sure that nothing goes awry, even though we do have margin around each one of these hazards. So what I thought I would do is go through each hazard as we see them here and then explain what we've done in brief with the sequence. So first we'll go with the radiation. As I mentioned, there's a peak of radiation that we expect to see inbound and then another one outbound. And then shown on this geometry, which is a figure of the Earth in the ultraviolet, I believe.
Yeah, we've seen this before to demonstrate, I think, that this would be the aurora around the, and this is the North America down here, and this is the Earth, and this would be the aurora around the Earth. And so that's the kind of thing I'm looking for at Neptune, but the aurora isn't your problem.
That's right. This just shows the
geometry. An interesting diagram. By the way, what's this?
That's the daylight side of the Earth.
Oh, it's not another aurora. This is the aurora, and that's just daylight.
Right, and it glows in the ultraviolet as well. But the point here is that you can imagine as Voyager goes across, it's coming in this way in this geometry. It'll sort of cut through this way, and what we're going to have as closest approach is about roughly right here, and then the occultation of Neptune starts shortly thereafter. And the radiation, you know, collects in the Van Allen belts, both inbound and outbound, and then the particles come streaming down and cause this aurora here. So there will actually be lots of measurements to measure what sort of particles are streaming down in that region when we get there. But it turns out that the biggest problem with radiation that we've experienced on either Voyager 1 or 2 is when Voyager 1 went through Jupiter, it went very close to the magnetosphere and got a really heavy dose of radiation.
Yes.
And that's sort of been our benchmark ever since, because that radiation was several times more lethal than what we can stand as humans, and for Voyager 1 it even caused a few things to get out of sync.
It sort of reset the clocks for
Yeah,
us.
there's a function in one of the computers that's kind of like resetting your stopwatch, and that only happens if there's sort of an electrical disturbance. And one of those computers was resetting and the other one wasn't, so the clocks got out of sync, and we lost a whole bunch of images.
They smeared.
Yeah, they were smeared because things were sort of out of control.
Spacecraft was moving when we clicked the shutter.
That's
Exactly
right.
the opposite of what we want.
Yeah, instead of panning and shooting, you were shooting as you were panning, and that comes in handy for some things like we're trying at Neptune, but not that case. So the whole idea here is that we wanted to see if our models could predict radiation levels lower than what we had at Jupiter, and we thought if we were comfortably lower, then we'd be maybe okay. So it turned out that there were inconsistencies in different observations that might have indicated that you could see a radiation field at Neptune. All these years, all this is based totally on theory and hypotheses about what might be there, and it really is hard to observe anything about the magnetosphere this far away.
But now we are getting a little bit of data.
We're getting data, yeah.
And you feel comfortable with it?
Yeah, and all these models, it turns out, were based totally on the best judgment of the experts and not on any observations. And these models appear to be bracketing what we're seeing now very well. So we don't really have what appears to be even a worst-case radiation environment.
Okay.
Well, we still don't know because we're not even in the magnetosphere yet. But anyway, what's happening is in the sequence, we actually have some preset times where these computers will reset themselves.
Regardless of whether or not anything's happening.
Yeah, the clocks will resync automatically so that even if things are slipping, it'll go back right before critical event.
Fixed it up. Okay, so we
Okay.
make it through the Van Allen belts, and next is the ring plane. What's likely to happen there?
Okay, the concern here is that we've known as you go through these ring planes, I think it's been detected at all three planets so far. A little bit at Jupiter, quite a bit at Saturn, and quite a bit at Uranus. You could actually, if you look at some data from the plasma wave instrument after the fact, they can run their signals through an audio synthesizer. And you can actually hear the particle impacts as you cross the ring plane of very fine particles.
Hitting on the antennas of the...
Hitting on the whole spacecraft.
On the whole spacecraft.
And each particle vaporizes if it hits the right way, and then this vapor is like a plasma wave, and that's what they're designed to detect on that instrument. So you hear those, and it sounds just like a hailstorm. And it builds as you come in, and for about 10 or 15 minutes, it
So you
builds and
anticipate
comes up.
something like that here, too.
Right, and so the model for Neptune is always assumed that if you go inside the ring arc region, you're going to be a little more dangerous, perhaps, taking more risk than if you went outside. And how far outside, we didn't know because we didn't know how these ring arcs were formed.
Right.
It's anybody's guess, so we put a fairly large margin on that. And the idea has always been that if we go far enough out from where we think the ring arc outer limit is, we're going to see some diffuse material, very fine particles that we've been through before, and even if we hear them, that's fine. They're not going to hurt us. So that's what we're concerned about inbound, and you'll notice from the distances here that inbound, we're very, very, very close to where the outer edge of the rings are. Somewhere about the end of that arrow is where the outer edge of the ring system is. Outbound, we have a little more pad, and I believe we're only about here with the rings, and we've got all this extra margin. So we've never really been worried too much about that. So I wanted to demonstrate a little bit about what sort of particles might damage the spacecraft.
Certainly.
Because various parts are built a little better than others for that kind of thing. So I brought a little portable ring plane crossing kit here.
Okay.
And I've got a few particle sizes. And the reason this is so important is because, you know, one wrong particle going the right place on the spacecraft could completely wipe out the rest of the encounter if it hits a critical computer or whatever. And the velocities that we're going at this ring plane crossing, we're already picking up speed. By the time we get here, we're not going to be going 37,000 miles an hour, but more like 47,000.
That's a
hefty
tremendous
increase.
amount of energy.
Tremendous amount of energy. The particles themselves are going to be coming in, you know, at a certain angle. You can predict that from where the rings are supposed to be. And if we go through each particle size here, I'll start with the biggest ones because those are the least likely, we think,
Okay.
outside this region. Why don't we bring the model over here?
All right.
Now, I'll hold these up, and I had to take my best shot at the sizes. These are all on the order of magnitude, factor of 10 of what we're modeling here. And first size, and I'll thank the cafeteria for these. These are...
Those are grapes.
Yeah, they're grapes, yeah, but they're actually Neptune ring particles for the next 5 minutes.
All right.
And what these are centimeter-sized particles, you know, 1/100th of a meter.
Mm-hmm.
And we've used these as a sort of a lower limit. If any particle this size or bigger ever hits the RTGs, the radioisotope thermoelectric generators, the model says, based on analyses that go back way back to Saturn when they were considering going through there, that these particles could actually damage the RTGs, maybe break the case.
That's like damaging a battleship.
Yeah, because they're built to survive a launch explosion. So
Yeah.
you have to imagine these things must have some considerable energy. And it turns out I converted this to the energy that a baseball would have at the same, you know, the same energy. And this would be equivalent to a baseball hitting the spacecraft at 2,700 miles an hour.
Which is a little fast for baseball.
Yeah, so if you threw a baseball that fast into the RTGs, you can imagine they might get dented a little bit.
All right.
Okay, so I'll dump
But you
these.
don't anticipate, however, that size particle in the
That's
region
the
we're
least
going.
likely, yeah.
Okay.
We've hardly ever really been worried about
What
that.
might we have?
Okay, there's two other levels that are still a hazard, but they get smaller. The next level is millimeter-sized particles.
We see that. That's BB shot.
Yeah, essentially. And these, you know, these are millimeters. They're pretty small, but we're still very worried about these. You wouldn't want these to hit the spacecraft.
Right.
They would, if one, for instance, hit the high-gain antenna, which is all a composite dish, they would go right through.
Mm-hmm.
And that wouldn't really hurt us too
Wouldn't
much.
hurt it, no.
'Cause,
But if they hit an electronics compartment, what would they do?
Yeah, and the key components that were modeled way back at Saturn, which we tracked, were the propellant tank. And if you have I'll get a pen out here. Propellant tank is right underneath the spacecraft.
Right.
It's sort of buried, so it's somewhat safe, but it's that round, spherical structure in there.
Uh-huh.
These things would go right through that,
That would
or dent them very seriously. yeah.
permit a bit of leakage.
Right. There's also, all the electronics are in these bays around the bus here.
Right.
And every one of those is potentially susceptible to one of these going right through the walls and into the equipment, and maybe splattering material all over in there as they shatter away. And the final concern for that was this size, anyway, is anything this small or bigger would actually damage parts of the scan platform instrument package here. Specifically, the cameras and the infrared instrument have these optical surfaces.
Yes.
And these things essentially would have the effect of sandblasting those surfaces because they're coming in with so much energy. So that's a very big concern, especially because we haven't taken all the great pictures of Triton yet,
Right.
inbound.
Of course.
So you really don't want to do anything to those surfaces. Okay, so let me put these back in their box. Okay, next size is essentially an order of magnitude smaller than the millimeter sized here.
Okay.
These are quite a bit finer. These are a tenth of a millimeter in size.
Okay.
Salt and pepper.
Salt and pepper, all right. We don't actually anticipate salt and pepper, but something that size.
But
Nor do we anticipate
methane
grapes.
methane ice that started to change to carbon looks a lot like this, I imagine. So anyway, those are very, very small, very light, and the concern with these is, again, a sandblasting type concern, and the parts that we're worried about are this target plate right here on the spacecraft is
calibration plate.
very critical after the encounter. We need to have that look the same as it did before encounter so we can calibrate the cameras and other instruments. And also these thermal louvers, which are very small window pane,
Silvery
mini
things on
blind
the
type
side, yeah.
windows for automatically controlling temperature. They're just thin, double-walled aluminum plates, basically.
But they have to have the right kind of surface on the outside. They have to shine, essentially.
That's right, and these things could essentially abrade those and maybe make them duller and not work as efficiently, which would cause temperature problems, which causes receiver problems, and you wouldn't want that either. So that's like the lower limit of particle sizes that we're worried about. Let me dump these here.
Dump.
Salt and pepper on the grapes.
Right.
Okay. Now the final is, I'll give you an example since we're going down of what we consider safe particles, and these are the kind we might want to we might pick up on this instrument as we go through. And
Typical of what we've picked up previously.
yeah, it's roughly the size, and this is just the creamer you put in your coffee. And
Very
these are
fine powder.
very fine powder, maybe 10 times smaller than the salt and pepper particles,
Okay.
or even less than that. It's kind of hard to tell. But if this stuff hits the spacecraft, which we expect we'll have, we'll hear that eventually when we process those signals. And again, it'll sound to us like a hailstorm when you do that, because every one of them is impacting and vaporizing. So
Damaging?
no, not enough to cause any degradation in equipment. You may find, if you could ever find Voyager later, that maybe some booms were slightly discolored or something. But
This wouldn't hurt the optics and...
well, we don't want to take a chance.
Oh, well, what do you do?
Well, what we've done is, since we're not sure that
Right.
these are the only things there, the idea is that we'll take a safe position anyway, and just take the platform before we go to ring plane crossing. Several minutes before it actually gets to what we call a safe parked position. And we, instead of looking at Neptune and the rings and Triton, we just move it the other side. And we turn it over the shoulder of Voyager away from these incoming particles. It turns out it's about 80 degrees away from the incoming stream.
But that limits what you can take pictures of. And
Right, and I have some examples of the really neat pictures we had to throw away because of this. But it's essential to keep the camera in good shape, we think.
Okay.
And you don't want to take any chances since you don't get here very often. So we'll call up the first one. Now this is very close to ring plane crossing, and we've actually enhanced the rings because they're modeled like we think they are, so that we really wouldn't see them much in this image. But if we could have gotten a really good picture coming inbound of this ring system like this, all the way out. And this is just the type of geometry we're going to get on the outbound leg now,
Okay.
in forward scattered sunlight. But you would love to get that inbound as a comparison, because they'll look different. And because this is so close to the inbound ring plane crossing, and because we didn't know when that time was occurring, because of this pole tilt uncertainty, we had to basically park the camera a lot earlier than this. So we just couldn't get this image anymore. And you'll notice there's a really interesting alignment. It turns out that in the lower left limb of Neptune as we go inbound, just about a minute or two after that picture I just showed, let's not go that fast. Okay. Right here, this arrow is Triton. And that's
Okay.
our target after closest approach. And Triton right now is because of the movement of the spacecraft, is actually setting behind Neptune.
Okay, let's see that next picture. That we
Okay,
had
so the
on-
next picture focuses in right on this geometry here, about a minute later. Let's go to that now.
Go back to that picture with the Triton just off the limb we had up a moment ago. The picture after this in the sequence.
There we go.
There we are.
And at this point, as I mentioned, we're going about 47,000 miles an hour, which is really fast. And it only takes about 1 minute for Triton to essentially set behind Neptune. So even if we could point our camera, that's kind of a tricky picture to get.
Yeah, yeah.
But it's a really nice picture.
But we won't
We
see
won't
that
get
one.
that.
Okay.
Now, what we will get, we sort of had to make the best of a bad situation. So the next picture shows some of the ways we're getting at least part of what we wanted.
Okay.
Right before we cross the ring plane, we would like to get the best shot of Triton we can possibly get, just in case something happens, because
Okay.
we're going through all these hazards. So this is the best picture we'll get of Triton Thursday evening, right before we cross the ring plane, the radiation, the atmosphere.
Okay.
If
So it'll fill the frame.
that's right, it almost fills the frame. It's going to be a spectacular picture, but not as good as the ones afterwards. But you don't want to.
This is insurance.
Insurance, yeah. You'd like to at least get something this good. So we got that. Now the setting Triton, we couldn't get inbound, but it turns out about a half a Triton orbit later, when we're past the planet, it goes around its orbit and essentially goes behind Neptune from our point of view, and then comes out the other side again.
Oh, do we have how?
And we've got that picture sequence. This is it coming out. A lot of people are thinking on the team that this may be one of the best pictures we'll get of the whole encounter, because it is a nice geometry. The crescents are showing.
Beautiful.
Our space model shows one of these spots that's been discovered right here, and who knows if that'll be there then, but it's nice to think about it anyway. So anyway, we're trying to handle this ring hazard as best we can by just taking the pictures at the latest possible moment. So with that, we'll go back to the next hazard, which is the last one I want to talk about. Okay, we passed the ring plane inbound. About an hour later, just a few minutes before, we start getting into a region where if for some reason our trajectory was too low, we could start hitting the fringes of the atmosphere. And the real big concern there is that you'll notice the closest approach is there where we hit this atmosphere hazard.
Yeah.
Only a few minutes later is when this all-important limb track maneuver starts for the occultation experiment. Very complicated. We have to start it within 1 second. The spacecraft has to be really quiet when it starts. And we've always been concerned about getting some perturbation from the atmosphere and causing the spacecraft to bobble and never quite recovering by the time it starts.
So purely atmospheric effects. That far up, 3,000 miles above the cloud?
No, not there. We're safe where we are now.
Oh, okay.
To our best guess, but years ago, we didn't know what the atmosphere was like there. So we tried to bias the trajectory out so that we could never get into a hazardous region. But just to understand what that region was a very big problem. Because
But now you're confident that we'll make it through that?
we're not very concerned about this anymore. But a year ago, we certainly were. And it turns out this is a new problem for Voyager at this planet because we've never had to go so close before. And we had to, from scratch, analyze the torques on the spacecraft and everything. So.
Are we going so close because of the need to get the gravity bend to Triton? Is that what
primarily
demands
the... Yeah. In fact, about 3 years ago, the trajectory was actually trying to get about 4 times closer to Triton.
Mm-hmm.
And then all of a sudden we had one of these physical constants updates, which drive most of these models, and everything changed for the worse. The pole tilt tilted backwards, and so the ring plane was right in our way. We were going through the rings. The radiation got worse. The atmosphere, Neptune got bigger. The atmosphere got hotter. The atmosphere was right up in our path. And so that's why we went out to 40. And it was all driven by these hazards 3 years ago. And ever since, we've been trying to take more careful looks at these things. So, but based on our trajectory, we're right on the money. We have plenty of margin in all these hazards. We're going to be close, but not too close. So that's what we're all counting on.
Very good. But we'll go back out. We'll go again through a radiation zone, but weaker or similar?
Well, you can see the peak radiation zone inbound is this contour right here.
Yes.
We go right through that if you believe our model, which we'll be off a little bit. Outbound, we just kind of clip the edge a little bit.
So outbound, both the rings and the radiation zone problems are less than inbound.
Right, and what our model tells us, and we still think this is fairly accurate, is that inbound, well, if you count the whole trajectory, inbound is the worst peak flux, as we call it, the actual peak radiation level, and we estimate that'll be about 57% of what Voyager 1 saw at Jupiter, which we consider safe. But the real important thing in some of these concerns is how much radiation you get over the whole trajectory. And compared to Jupiter, it's only 3%, which is almost nothing. And that's the one, it's in the noise almost. So because of that, we're not too worried about radiation either.
Very good.
Now, the last thing that we can use to summarize all this is that movie.
Fine. I think we did put together a computer-generated movie that shows how this whole procedure is going to go.
And we'll just start basically where this diagram starts here and just carry it all the way through.
There we go.
And right now we're just about to enter the ring plane crossing. By this time you can see the platform is already pointed backwards. And we cross the ring plane. Here's the arc right here. This is about the time we'll hear these noises eventually when we process the data. And we're picking up speed like a bandit right now, peaking at something like
47,000 miles.
Yeah, 61,000 miles an hour at closest approach. Here's where the atmosphere hazard comes in as you go by the planet. And as you fade away, you get another ring plane crossing eventually. And it's at this time, that we think if we can make it through all this, we're all set to get ready for Triton, which is what the spacecraft's doing right now. So,
very good.
Should be exciting Thursday night and Friday morning. Watch all this happen.
We'll watch all your predictions come true. Thank you very much, Rex. Right now, Voyager is conducting a photopolarimeter observation of the planet in order to determine the particulate scattering properties of the Neptunian atmosphere. We have further infrared and plasma wave studies planned for this afternoon as well. So, the Voyager Update, I'm Al Hibbs.
space mission, which in the past few days has carried the eyes of men farther than they've ever been.
And the science is pushed in in an amazing way.
Just
It's
last
like
night,
fitting a jigsaw puzzle
we
together.
had these frames come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour.
Good afternoon, and welcome to the 3 o'clock edition of Voyager Update. I'm Donna Pivorato, and I'm your host, and it's 3 o'clock p.m. Pacific Daylight Time. The Voyager spacecraft is 1,865,000 kilometers, or 1,159,000 miles from the cloud tops of the planet Neptune, and falling towards the planet at a speed of 37,932 miles per hour relative to Neptune. With me today is Norm Ness of Voyager's magnetometer team. Welcome, Norm. And you're going to tell us first, I think, something about where the magnetometer is on the spacecraft and what a magnetometer is, as a matter of fact.
The problem in making measurements on spacecraft, which is really like a portable laboratory bench, a research laboratory, but robotic, being unmanned, is that the laboratory bench itself can contaminate the measurements in various ways. And in the case of the magnetic field measurements, because there are electrical currents flowing on the spacecraft, we have to use a very long boom. This boom is about 40 feet long, to place 2 magnetometer sensors, one at the extreme end, one about halfway down the boom, to make simultaneous measurements of the magnetic fields in space.
So this whole thing is just to keep the little black boxes away from the spacecraft at different distances.
That's part of the story.
Okay.
The fact that there are 2 of the magnetometers is so that with the simultaneous measurements at 2 different locations relative to the spacecraft, mathematically approximating the magnetic field of the spacecraft based upon ground testing, we can take out in real time the dynamic spacecraft magnetic field, because the currents change, because there are manipulations of the scan platform, and so on and so forth. The spacecraft magnetic field is not constant. At the present time, we're measuring a magnetic field that is less than 1/1,000,000th that of the magnetic field on the Earth's surface. That's the magnetic field in interplanetary space. The spacecraft magnetic field is about a factor of 3 to 4 times larger than that. So if we didn't have the dual magnetometer technique available to us, if we didn't have this long boom to put 2 magnetometers separated this radial distance from the spacecraft, we would be very handicapped in making measurements in the interplanetary medium.
So you're trying to pull a very small signal out of a lot of noise, and this helps you recognize the difference between the signal and the noise.
Yes, indeed.
Okay. Well, let's see. As we come in toward the planet, we're starting to get some magnetic effects pretty soon, and I think we have a tape that will show how the spacecraft's approaching the planet. So can we roll that tape? There it is. Okay, here comes the spacecraft in from the right side. So what are those yellow lines?
Well, those yellow lines are approximating the shape of one of the boundaries that is characteristic of the interaction between the solar wind and the planetary magnetic field. We'll have a bit more to say about the physics involved there. The position of these boundaries is indicated as somewhat uncertain, and that uncertainty is related to both our lack of knowledge precisely of the magnetic field of the planet Neptune, and also the uncertainty associated with the strength of the solar wind at the time that we make the crossing of that particular boundary.
Okay. And we've got a piece of hard copy that you can use to talk about that. Let's see. Is it up on the telestrator? Yes, it is. Okay.
That diagram is a sketch which some of your viewers have probably seen already in this series of presentations. And what this shows is the planet, the dipole magnetic field lines of force deflected by the solar wind, which is coming, in this case, from the left-hand side of the screen. And at this surface, which we call the bow shock wave, the solar wind is deflected so as to no longer flow radially away from the sun, but to flow around this obstacle that the magnetic field creates. This is a magnetic barrier to the flow of the solar wind. That is, the magnetic field deflects the solar wind being composed of charged particles, primarily protons. There's a second boundary associated with this interaction, and that's this magnetopause. That's where the solar wind is not only deflected but prevented from penetrating into this magnetic cavity, this magnetosphere, and then behind the magnetosphere is this magnetic tail region.
Okay, and your instrument is going to measure all of those things.
We expect the measurements of the magnetic field to begin to become interesting when we cross this bow shock wave, when the presence of the planet will first be displayed to our instrument.
Now, Tom Kermegis yesterday and Jim Warwick the day before were talking about they expected to see some sort of charged particles as affected by the magnetic field about now. Is any of that happening?
The situation is that there are, in a sense, precursors possible to the interaction of the solar wind with the planet beyond the bow shock, that is further away from the planet, if the interplanetary magnetic field has the correct orientation. If the magnetic field connects with the bow shock to the spacecraft, then waves and particles can propagate upstream, and you will detect them with the spacecraft. But at the present time, and in fact for the last several days, the interplanetary magnetic field has been very quiet and at an orientation appropriate for a very quiet solar wind condition, namely perpendicular to the planet sun line, just the wrong direction to observe any upstream phenomenon.
I think we actually have on Vanessa a picture of your real-time data.
Yes.
And we can see if anything's happening.
What we have shown here in these 4 traces.
You have to push. There you go.
4 traces represents 4 ways of recording the phenomenon we are observing. The lowest most scale is the magnetic field magnitude. The next 2 curves show the latitude and longitude of the magnetic field vector, the magnetic field being a directional quantity.
Relative to the planet?
No, we're using a coordinate system, in fact, which is related to the sun. We call it a heliographic coordinate system because all of the phenomena in interplanetary space that are not directly coupled with the planet, obviously, are driven by the sun, the sun being the controlling parent body in interplanetary space. These funny dropouts that are readily evident in these 4 places correspond to gaps in the data associated either with data transmission from the spacecraft or some interruptions in the ground data processing system on the ground.
Okay, so they're not real.
No, certainly not real. If they were, they'd be a most magnificent new physical discovery. The field magnitude is running along at a very steady value. It's about 1/10 of a nanotesla. As I said, much less than 1/1,000,000th of that of the field intensity at the equator. The direction of the magnetic field here, the longitude, which is the principally important direction, is running around 90 to 100 degrees, measured relative to the sun, which means it's perpendicular, orthogonal. Again, it's in the wrong orientation for us to see any upstream events.
Now, another thing that Jim Warwick and Tom were talking about was the impact that the moons have on the magnetic field and the charged particles and so on. How will that show up in your data?
Well, that wouldn't show up in this data, but it will show up inside the magnetosphere. So if we could go to the next figure, there's a very interesting coupling which takes place between plasma physics and magnetospheric physics. This diagram shows how when you have these
We have it on the
regions,
telestrator if you want to point.
when you have these regions of trapped radiation indicated in this purple, if there exists a moon at one position, this moon is an absorber of these radiation belt particles. And because the motion of these particles is to travel along the field lines, bouncing back and forth, this moon is an absorber which creates a hole. In fact, it's a very special kind of hole. It's sort of a loon which wraps completely around the planet. And this hole in the radiation belts is useful for studying the configuration of the magnetic field. In fact, Because we make measurements only along the spacecraft trajectory, which is shown in this orange line, we have to do a complicated mathematical analysis to determine what the magnetic field will be away from the spacecraft trajectory. We have no way of checking the validity of that mathematical model except by a test with some other independent process. And the other independent process is the existence of radiation belts, their motion, i.e. their structure, being controlled by the three-dimensional geometry of the magnetic field, permits us to ascertain when we take our mathematical model and predict, knowing the position of the moons of the planet, where these holes should occur, whether or not they in fact occur when they are observed,